In this video, we are going to take a look at what is called experimental error. Now, in some ways, experimental error might be what you think it is, but in some ways, maybe not. So we're going to take a look at some examples because a lot of times at the end of labs, a lot of questions you'll be asked are what are some sources of experimental error? And so you want to be aware of what they are and so that you can try to minimize them in the future. So here's our definition. An experimental error is an aspect of the design of the experiment. So notice design is really a key word here. And there are aspects of that design which will cause your results to be off. Now, off's not a very official word. Probably a better word to use would be inaccurate. Remember, accurate is your answer correct or on the mark or not. So these are things that mess your results up a little bit. So now, when we ask you to list your sources of experimental error, we're not dooming your experiment to failure because every experiment has sources of experimental error. Whether it's an experiment that as a high school chemistry student you're doing, or whether it's an experiment that a NASA scientist is doing, all experiments have some sort of experimental error. Now, the difference between a good experiment and a bad experiment is that a good experiment has very little experimental error, whereas a bad experiment has a lot of experimental error. Now, it's not only good to be able to, after the fact, go and describe your sources of experimental error. It's even better if you can anticipate them beforehand when you are designing the experiment. Because if you can anticipate what they are beforehand, then you might be able to come up with some things to do during the experiment to minimize those sources of experimental error. And if you can minimize those, then hopefully you'll get a better, more accurate result in your experiment. So before we get to examples that are sources of error, I want to talk about some common things that are not experimental error. We call these things blunders or mistakes. These are not part of the design of the experiment. Okay, a blunder or a mistake is some kind of a goof or an accident that happens during the lab. A lot of times when I get people, if I ask them what experimental error, sometimes they'll say, well, we measured wrong. Well, that's not a source of experimental error. Yes, it is going to cause your results to be inaccurate, but they're not part of the design of the experiment. It's not like step number 3 says, record the mass of this beaker, and oh, by the way, make sure you measure wrong when you record the mass of this beaker. Okay, so that is a goof. That's a blunder. It is not inherent in the design of the experiment. Another one that I get sometimes is, well, maybe we calculated wrong. Again, this is not part of the design of the experiment. It's a goof. It's a blunder, which, by the way, should never happen when you're working in lab groups because it's easy if you're working by yourself to make a calculation error and not know it. But when you're working in your lab groups, I should never see calculation errors because you each should be doing your own calculations and then you're verifying your answers with each other. And while one person might be able to make a mistake and accidentally punch in a wrong button, if I'm doing it and my partner's doing it, we're not accidentally going to make the same mistake and accidentally punch the wrong button. So we'll get different answers. So then we'll know to go back and double check our work. So not only is we calculated wrong not a source of experimental error because it's not part of the design of the experiment, but it's something that shouldn't happen when you're working in groups. Another case, well, we spilled some of our sample. Again, that's a blunder. That's a mistake. It's not like step 4 said, all right, carry your sample back to your table and trip and spill half of it on the floor. Okay, that is a blunder mistakes. Another one's just another misuse of the equipment. Maybe we forgot to press tear on the electronic balance. Okay, you're right. That's not going to make your results good, but that is not inherent in the design of the experiment, and thus it is not experimental error. Okay, another thing that sometimes people mention is that, well, when we make measurements, we've learned in Unit 1 that all measurements, the last digit is guessed. So there's a little bit of uncertainty due to that last digit being guessed. And so because of that, we're always going to have a little fluctuation in our answers because of that uncertainty. But that's just a minor amount, and that's just a constant way that we do things. So if I ask for sources of experimental error, don't say, well, we guessed at the last digit, because that's just inherent in the way we make measurements. And if you do get 2 answers where the last digit is off by 1 or 2, we don't really even consider those different answers. So let's look at some examples of things that are sources of experimental error. Now, sometimes, because we are humans, we have to make judgments, and we have to kind of guess a little bit at measurements that we're making. And because of this, our results are not perfect. Let's say, for example, we're using a stopwatch to time things. Let's say we decide to time how fast our Hot Wheels car is going. So we're going to move our Hot Wheels car, we have our stopwatch, and we're going to click that stopwatch when it crosses the start line, and we're going to stop the time when it crosses the finish line. Okay, so we let it go, we do our thing. Well, because we're humans, we're probably not going to be perfect in exactly when we clicked that stopwatch. We might have started it a little early, a little before it hit the line, or maybe a little bit after. So my results aren't going to be perfect. Just because I'm human, my reaction time is not going to be perfect. It doesn't mean that this is a bad experiment. It doesn't mean that that's wrong. It just means, well, my answers are going to be a little bit off because of this. So that's one example of experimental error, reaction type thing. Another case of human error where we have to make a judgment is maybe we're trying to note the melting point of a substance. I want to know, well, what temperature does it melt at? So usually what we do is we put them in these little tubes. We put them in a little kind of mini oven, which heats them up so we can see the temperature displayed, and then we look, see, well, is it melted yet? I don't know. Okay, well, now it looks a little different, but is it melted yet? I don't know. And all the while, the temperature's changing. Is that melted yet? I don't know. So at some point, we have to make a judgment call, and we have to say, okay, now I think it's melted. And then we also have to look at the temperature there. So, maybe you made the call a little too early. Maybe you made it a little too late. You're going to be off a little bit because of that. Maybe just a reaction time of looking up at the temperature between the time that melted was a little bit slow. So that'd be another source of error. Maybe we just didn't call it at the right exact point. Okay, another case of experimental error is what I call difficulty in measurements. Now, this is not the same thing as we measured wrong. We measured wrong is you've got a goof, you've got a blunder. But there's some measurements that are just legitimately difficult to make, and there's just something about them that it's really hard to get a good, accurate reading on. Let's look at some examples here. Let's say I was trying to measure how high up this muffler was in this car. So, I take my meter stick, we prop it up like we say there, and that's kind of a tough measurement there because, number one, the object that I'm measuring is a little bit rounded, and trying to figure out exactly where the bottom edge of that is, I can't line this ruler up too well if I'm doing in between here, and so I have to try to eyeball where the level is, and that might be a difficult call to make because of the irregular shape of the object. Well, another thing is if you look at the way we have to line this up is that if my meter stick is not straight, well, that's going to mess up my results. I'm not going to get the exact height. If it's leaning in, like in this case, it looks like it's leaning in a little bit this way, or if it's leaning one side to the other side, then I'm not going to get a perfect answer. Okay, in fact, you can actually predict which way your answer is going to be. In this case, if my ruler's not straight, what's going to be true about my answer? Think about that for a second. If you said that your answer was going to be bigger than the actual height, you're correct. No matter which way it's tilted, that error is going to cause you to get a bigger answer. And that's something that oftentimes we'll ask, if we have this error, what impact is it going to have on the results? And sometimes you can predict, such as in this case, well, that error will always give me a bigger answer. Other times, it's impossible to predict, like with the stopwatch. It's impossible to predict whether we're going to have a bigger or a shorter time. It just depends on how we guessed. Here's another example of a difficult measurement. Let's say we wanted to measure the diameter of a balloon. So we take a ruler and we line that ruler up and we kind of eyeball where the edge is. Well, that's a difficult measurement to make because that balloon is not flat. Rulers are designed to measure objects that are flat. And so you kind of have to eyeball the edge of the object is pretty far away from the ruler. And if your eye is looking at a little bit of an angle, you're going to get an inaccurate reading. So it's just difficult to have everything lined up and be able to tell exactly where the edge is. Not that it's wrong to do it that way, it's just that's a little difficult. Another thing is, well, where do you hold the ruler? Technically, diameter is where we cross the center of the circle, so you're probably just eyeballing that ruler and trying to guess, okay, I think that's about the center. Whereas if you're holding your ruler a little bit high or a little bit low, you're going to get can you predict which one it is? Bigger or smaller diameter? Well, if you're not at the center, it doesn't matter whether you're high or below the center, you're going to get a lower diameter than the actual diameter of the balloon. Okay, so that's another, it's difficult to line it up. Not wrong to do it that way, it's just a source of error for the experiment. Sometimes when we're making measurements, we have to assume some things. We might not be able to get the exact measurement that we want to. And so we have to make some assumptions. And again, I call these false assumptions, but it's not like these are wrong. It's just they're assumptions, they just aren't 100% true. Maybe they're only 98% true. So it's the best way I can do it. So it's not wrong to do it that way, but we do have to just realize that, hey, this is not going to be 100% accurate. Let's say I wanted to know how far away my house is from school. So if this is my house and I drive to school, I might set my little odometer and as I'm driving, measure the distance that it takes. And so when I get to school, the odometer says 6.7 miles. Well, I have to realize that that's not the actual distance my house is from the school because, number one, I had to drive on the roads. So the actual distance that my house is from the school is going to be different than that. I'm going to have a little experimental error. Now, can you predict how's my actual distance going to compare to what I got with my odometer? It's going to be greater or less than. What do you think? All right, well, if you said the actual answer is going to be less than 6.7 miles, you're correct, because obviously I drove on the roads, and if I were able to drive in a straight line, I would find that the actual distance is a little bit shorter than the distance that I actually drove. So, again, if those are the best resources I have, maybe that's the best way for me to measure this. Now, maybe I can find some other things. Maybe I can get some satellite images and make measurements from there, or maybe go up in a helicopter and do a laser survey. But maybe those aren't at my disposal. So I have to make that assumption. That's the best way I can do that. Let's say for another example that I wanted to find out what the volume of that balloon is. Well, I think about how I can do this. It's too big for water displacement, at least in our equipment that we have. So I can think, well, let's use a little geometry here. That balloon, I can use my 4/3 pi r cubed because that's the formula for the volume of a sphere. So we go ahead, we measure the radius of the balloon, I pop my radius into that formula, and I get an answer for the volume. Now again, I'm asking you, there's going to be some sources of error there. So is your answer that I get using that formula, is that going to be greater or less than the actual answer? Think about that for a second. Well, if you said your answer was going to be less, you would be correct, because when we measure this radius and pop it into this formula, it gives us this volume of a perfect sphere. Well, the balloon is not a perfect sphere. In this case, it's a little bit bigger than that. So the answer we get for the formula is going to be this yellow shaded area, but the actual balloon volume is actually bigger than that. Again, that might be the best way that I have to try to figure that out. I might not have any other equipment, so it's okay to do that way. I'm just not going to have a perfectly 100% correct answer. It's an assumption I'm making. It's not entirely true. Another assumption, let's say that we had some metal that was in some hot water. So here's our hot water here, and I want to know, well, what is the temperature of this metal? Well, I can stick a thermometer in there, but I can't, stick a thermometer really inside the metal. So what I can do is I can make an assumption. We can stick the thermometer in there, but really the thermometer is not measuring the metal, it's measuring the water. But we can assume, well, if that metal has been in the water for a long time, then the metal should be about the same temperature as the water. So I stick my thermometer in there, measure the temperature of the water, and we can record that then as the temperature of the metal. We're making the assumption that the two are the same. Again, it's not wrong to do this. So one last thing, I don't know if it's the last thing here, but another thing that's a possible source of error is what I'm going to call varying unvariables. When you are doing an experiment, there should only be one condition that you are changing from trial to trial. All the other variables should remain constant. Okay, it's called isolating your variables. In a valid experiment, you should always be doing that, where only one thing is changing. So, but sometimes things beyond our control will change, that we have no control over, or maybe things that we didn't think about. So for an example of varying unvariables, we're going to take a look at an experiment, and let's say that we want to see, does adding Miracle Gro to plants make my plants grow taller? So we're going to take some plants, and some of them will give some Miracle Gro to, some will give a little bit more, and so forth. So that's my variable. And we'll set them out, we'll let them grow for a while. And now just think about this setup, and what I want you to do is pause the video for a minute and just sketch down some things that might be changing that should not. Now in our experiment, the variable is how much Miracle Gro the plants get. So in our experiment, the only thing that should be different from plant to plant is how much Miracle Gro they get. Everything else should be the same. If something else changes, then that would be what we're calling a variable unvariable. So pause it, see how many things you can write down, and then click again to play. All right, so here's some examples that I think are some common answers here. Now, one thing by the picture, you can see that it looks like, hey, some of these plants are near the window and other plants aren't. So one thing that might be different is they get different amounts of light. Well, again, the only variable here should be how much Miracle Gro they get. So if some get more light than others, that's definitely a source of error for my experiment, and I don't want to do that. Another possible thing is I would need to make sure each day that I'm giving every plant exactly the same amount of water. We want that to be the same. Some things is, how much soil are they in? What type of soil? Did I make sure that they all had the same amount of soil and the same exact type of soil? If not, that would be a source of experimental error. That would be something that's varying that should not be changing. Another example is, well, maybe since the sun's here and this is absorbing the sunlight, this side of the room might be a little warmer temperature-wise than the other side. And maybe at nighttime it gets a little cooler possibly because it's by the window. So it's possible that the plants might be exposed to different temperatures. And again, that would be something that would be varying that should not be. Again, you want to isolate your variable. The only thing different should be how much Miracle Gro did these plants get. The rest of these would be all sources of experimental error. Another example of a varying unvariable would just be, in the course of carrying out an experiment, your room temperature might fluctuate depending on what you're measuring. If I'm measuring the volume of a balloon, and I measure it one time and it's warm in the room, and I'm measuring the volume of a balloon 2 hours later, well, if the room temperature dropped, then that's going to be another variable in my experiment. So some of these things are just out of control, beyond your control. Maybe the air pressure in the room is fluctuating from day to day, and that might mess your results up. So all those things are varying unvariables. Another one I'll mention briefly is contamination of chemicals, and this one's kind of a blunder. I'm not sure how much of it's true experimental error, how much is really a blunder. I'll list it as experimental error because you might not have been the cause of it, or you might not even be aware that it's happening. But it's important when you're doing chemistry that your glassware is clean, because a lot of times if there's some chemicals in there, it will totally mess up your results and give you different results than you would because of the presence of those unwanted chemicals. Sometimes the chemicals that you're using in lab just get old and change. Maybe they've gotten contaminated by some previous course, or a lot of things when you leave the lid on them, they'll absorb moisture from the air and they'll start to react with that. And so they're no longer the pure chemical that they used to be, and so they're not behaving like they would. So that might mess up your results, be a source of experimental error. Or as we said, some other people maybe previously who used it, they didn't clean off their spoons or the spatulas that they were using, and so they contaminated the chemical that way. That could potentially mess up your results. Another interesting one to think about is a lot of times just in the process of making a measurement, you actually mess up and change that factor. And here's a good example here. If maybe I stick a thermometer in some ice water to try to figure out what the temperature of my water is. Well, so I get my thermometer, which has been sitting out in the room. I dip it into the cold water. Well, I've actually just changed that water. My thermometer is warmer, and so just the actual glass part of the thermometer is going to add energy to that water. So I've actually changed the temperature of that cold water by sticking the thermometer in it to measure it. That's probably not a big, huge amount, but nonetheless, it's a source of experimental error. Another example is when you are making and taking samples. Your sample might not be a true representative of what you're testing. So we'll call it an unrepresentative sampling. Maybe I want to figure out if a river's polluted or not. And so I just go out, I just take a couple samples, but it just so happened that when I took the sample, I took it near a golf course. The golf course just laid down a whole bunch of fertilizer the previous day. It just rained, so a lot of that fertilizer just ran off into the river. So the sample that I'm going to get is going to be really, really high in pollution, and it's not normally that bad. I just happen to have a bad sample time. So that would be an unrepresentative sample. Maybe if I'm doing a survey, I want to know who's going to win the election, so I just call people during the daytime. Well, that's going to be not a true representation, because I'm probably going to get people who maybe aren't busy at work, and so I'm going to get a biased survey in that case. Or maybe I'm going to get people that just work second and third shift, and so I'm not getting a true representative of the population if I do that. Maybe I've got some unknown kind of liquid. Not sure what this is here. Wouldn't want to drink that. But if I'm trying to measure the density of this liquid, and all I ever do is just dip a little eyedropper in and pull a little bit off the top each time. Maybe I even do a bunch of trials, but I'm just pulling it off the top every time. Well, that's not going to give me a true density, because this top layer here is probably less dense than the rest of it. And so I'm not getting a true representation of that in this case. So when you are taking your samples, there are some things you can do to minimize this unrepresentative sampling issue. One thing, we always do mini trials. Our idea is we want to get the best average. So if we do a bunch of trials, hopefully we'll get a good answer there. When you are taking your samples, you don't always necessarily want to do the same thing. You want to vary it up a little bit. If it won't affect your results, change your sample size. Change your location. If I'm monitoring a river, I would want to pull samples from different parts of the river, or maybe take my samples at different times of the day instead of always taking them, in the morning. So those are some things you want to change so that you're getting a true average, a true representative. And you want to, again, just think about that. Do I have any possible bias in the way I'm doing things? Because that could mess up your results, make them inaccurate. Okay, so what we want you to do now is in your packet, you have this exact scenario. This scenario should sound awful familiar to you. And so I want you to read through the procedure, and you've done this, so think about it. And on the next sheet here, I want you to think, well, what are some possible sources of experimental error in that process? And in this first column here, I want you to list specifically as many as you can. See if you can come up with at least three sources of error here, and then not only list the source of error, but see if you can list the effect on the result. Is this error going to make your answer bigger than it should be? Or is this error going to make your answer smaller than what it should be? And don't forget, in some cases, it might not be able to be determined, so you might have that as well. So you've got two scenarios, the one with the rock, and you also have the one with the penny that's on here. So read through that for how we calculated and determined the volume of that penny, and see if you can come up with some sources of error for that.